Now, based on these described 4 processes, I want to draw PV diagram. Now, can you draw a PV diagram? First, let's not worry about TS diagram at this moment, but can you really draw the PV diagram based on what we just discussed about what really happens in real, 4-stroke spark ignition engine, and what he just described about 4 processes for ideal Otto cycle? Please pause this video and try to draw a PV diagram by yourself. Okay, I hope you now, are done on sketching your own PV diagram. So let's try to do it by together. So let's just make a certain boundary. Okay, so that is your kind of the smallest volume or clearance volume. So basically, that is clearance volume. Okay, and also there is another kind of volume that is maximum. Okay. Okay, let me just write down here. So there is a V minimum, but that is essentially the clearance volume. Now, from very low pressure, like atmosphere pressure, I would say, okay, so that is your position 1. Then during the first process, which is isentropic compression process, your volume shrinks from Vmax to Vmin. So now in the case, but that is isentropic process. And I'm gonna draw like that. So that is number 2 after compression process. Then that is isentropic compression process, which is constant entropy. Okay. Then from 2 to 3, we have constant heat addition process. So it should follow the direct vertical line. Right, so that is number 3. Then from 3 to 4, we should go through the isentropic expansion process. So now we also have this kind of expansion process here. Then that is 4, and from 4 to 1 that we have isentropic, constant volume heat rejection process. And now that is where we have heat in, and that is where we have heat out. Okay, and during from the 3 to 4, that is also, and let me just, that is S is constant. Okay, and as we already discussed this part, but how we can draw this isentropic compression or expansion processes in a PV diagram when your working fluid is an ideal gas. Okay, so let me just write it simply for ideal gas. Okay, let me write it here: ideal gas and constant Cp and Cv. Okay, now isentropic process gives us the relation of P and V as this, right? So from this relation, what you can see is that that curve should be a curve that represents P proportional to 1 over Vk. Okay. Now, the Vmax is same as V1, same as V4, right? And the V minimum is same as V2, same as V3. So that is the how we see in terms of volume relations. Okay. And at the same time, because we I already explained that this whole ideal Otto cycle should be based on the closed system, perspective. Now, the same volume means that same specific volume for 1 and 4, and same specific volume at 2 and 3, right? Now, from this relation, okay, the first thing is that how can you draw graphically, how can you draw the net amount of work that can be done by this Otto cycle? The answer is the area surrounded by these four processes is your net work. Okay. Then from that relation, your compression ratio, R, can be written as V max over V min, or V1 over V2. Okay. Same as V4 over V3. Okay. So that is, again, very important design parameters of the engine. And now, how can you draw TS diagram? Okay. So for in the case, expansion and compression processes would be very simple, okay, because that is isentropic process. So it should be somehow in kind of in the vertical line. So let me just draw in the case boundary. So we can start from this position to this position, right? And now from 1 to 2, let me just, from 1, that starts at almost room temperature or pretty low temperature. And to 2, we have isentropic compression process. So you should go up, following that vertical line, and that is 2. Okay. So the question now is that how can you draw the constant volume heat addition process in the TS diagram? So we haven't discussed this part yet. Now, so let's move on to this question. So how can you draw the constant volume and even the constant pressure process in the TS diagram? So now let's think about this part. So again, I'm going to use the ideal gas and also constant CP and CV. So let me just write it down for ideal gas and constant CP and CV with these two questions, the conditions. What we know is we can calculate S2 minus S1 as CV natural log T2 over T1 plus R natural log V2 over V1. Okay. Now, if V1 is same as V2, so now again, I'm talking about the constant volume process. Then the second term is basically gone. So what we have is S2 minus S1 should be equal to CV log T2 over T1. Or I can, because we are talking about how we can draw the T as a function of S, I can write it down as that. T2 over T1 is equal to, right, S2 exponential S2 minus S1 over CV. Right? So what it means is that now when we have slight change of from S1 to S2, your temperature is exponentially increasing, based on the S divided by CV. Okay, so now T is proportional to exponential S over CV. So that is for constant volume process. Now, what if we use this equation, S2 minus S1 is equal to Cp log T2 over T1 minus R log P2 over P1. Now, if P1 over P2, so constant volume, constant pressure process, then with the same kind of procedure, what it can conclude is your temperature in the TS diagram plot should be proportional to exponential S over Cp. Okay. Now, in TS diagram, okay, if you try to draw the constant volume curve and constant pressure curve, they should show us certain exponentially increasing kind of pattern or trend. But which one has higher slope? Constant volume process or constant pressure process? Now the hint is that which one between CV and CP is always smaller? So always CV is smaller than CP. So in other words, because there's all kind of expressed in terms of inverse of CV and inverse of CP, if you try to draw the constant volume process and constant pressure process together, there must be certain difference in the slope. Okay, and now that is constant volume process, constant pressure process, which is less stiff than the constant volume process. Okay, so that is how we can draw the TS diagram for constant pressure and constant volume processes when we talk about ideal gas and constant Cp and Cv. So even when you deal with working fluid which is not ideal gas, or which is, even though it has ideal gas, but that does not have a constant Cp and Cv process, that slope would be different, but the general trend in terms of the curve shape would be still the same. So now let's move back to TS diagram. So how can we, what I can draw for the constant volume process in TS diagram is that, right? So then that is 3. Then we have 3 to 4. Okay. Then we will go back to 1 with constant volume process. So that is how we can draw. So that is, that is constant, and that is also constant process. Okay. Then we have heat. Oh, sorry, that is not this way. Let me just draw it again. So that is here. Now it moves here and here and here. And then we have heat input and heat rejection. And net work can be expressed in terms of the area surrounded by these 4 processes. So now that is your net work. Okay? So that is how we can draw PV diagram and TS diagram for the ideal Otto cycle. I can give you a promise. I will ask you to draw, a PV diagrams or TS diagrams in the final exam. So please practice on how to draw those kind of diagrams for, thermodynamic cycles. Not only for this ideal Otto cycle, but all other thermodynamic cycles we are going to learn in the future. Okay, so promise me, please practice on this type of sketches. So for this lecture, we learned about really basics of the gas power cycles, and we moved our attention to the spark ignition engine. We talked about how spark ignition engine operates, by 4 strokes. Then we discussed the ideal Otto cycle, how we do thermodynamic performance analysis of spark ignition engines, particularly 4-stroke spark ignition engines, by having certain, the general assumptions. Okay, and we are going to learn more details about the thermodynamic cycle analysis of the ideal Otto cycle in the next lecture. But I hope that today you have a basically big picture of how we look at the spark ignition engines in general and internal combustion engines. So thank you so much for your time for this lecture, and I hope you have learned quite a bit about what we learned, what I discussed today. And see you in the next lecture. Thank you.